In this section, we're going to talk about colligative properties. Colligative properties are unique in the sense that these properties change depending upon the concentration of a chemical. So if we're looking at salt, or if we're looking at salt water, I should say, or carbon dioxide, or any other chemical, some of their properties can change depending on how concentrated they are, the amounts we have. Now, we're going to limit this to two simple properties: the temperature at which a chemical freezes and the temperature at which a chemical boils. Those are the only two colligative properties we're going to look at. Basically, here's what it is. We're going to look at how much temperature change occurs if we were to try to freeze or boil pure water versus salt water. So pure water versus salt water. And then even more specifically, depending upon the concentration of salt water, could also affect these properties. So what we're going to look at is we're going to look at a phase diagram and how that phase diagram changes once we add another chemical. So our reference point here is water. So what happens to water's freezing point and boiling point if we add something else to it? So here's a phase diagram, and this is one in your book. If you notice in the black, okay, this is the normal phase diagram for pure water. See if I can get this to curve a little bit. Nope, doesn't want to. Okay. 3 times the charm, didn't work. So you can see in here, here's our pure liquid, here's our pure solid, and then here's our gas all the way through. Okay. Normal phase diagram. But now if we look at what happens to water if we add salt to it, we notice here that the line between solid and liquid moves. It has actually dropped. So let's think about what we just said there. The temperature actually dropped. So a freezing point dropped if we add a chemical to that water, salt. Now let's look at the other line. Well, then here becomes the new phase line between liquid and solid, or sorry, liquid and gas water vapor. Now if you notice down here, the temperature at which the solution boils is now greater than what it was. So the boiling point increases or goes up. That's key. If you have a pure chemical water and then you add salt to it, the temperature at which it freezes will drop and the temperature at which it boils will rise. Very important. We can never make the freezing point go up for water, and we cannot make the boiling point drop for water. Basically what it does is it keeps the chemical a liquid longer. If you notice here in the middle, here's what I mean by making a liquid longer. The black is what the liquid was, that space. Now, if you notice, the blue is a bigger region for the liquid. So that's what we mean by makes a liquid longer. Okay, so here's our calculation. We want to find out how much does the temperature change if we're talking about freezing point or boiling point. And it's a simple calculation. It's K, which is a constant, times molality. Again, not molarity, molality. It's the only time we're really going to use molality. This is our calculation for the chapter, and that's it. All right? So that's the generic setup. So here's what it is. The K values is KF and then KB. Okay? So if we look here at KF, It is the molar point freezing depression constant, and Kb is the molal boiling point elevation constant. Here's the thing we just said. Remember from last page, freezing point drops, boiling point rises. So the freezing point depression dropping, the boiling point elevation. So these K values, first of all, for a particular chemical, they're never equal. And here's water's two values. So again, constants have to be given. I want to figure out how much temperature change occurs if I try to freeze salt water. Simply, it's going to be the change in temperature is going to be equal to Kf times the molality of the salt. How much salt did I put in that water? We do a molality calculation. If I wanted to look at the boiling point temperature change for pure water, I would take the Kb times its molality. Now, if you notice here, Kf is minus, Kb is positive. That goes in here with this because depression means delta T is going to be negative. Over here, Kb is positive, delta T will be positive. And that's what we're looking for in this calculation, is just a simple way to calculate the change at which the substance, the solution, will increase or decrease its temperature. And there's example problems and sample problems on page 449, 450, 451, and then on to 454 and 455. So you've got lots of sample from page, sorry again here, 449 all the way through 451. And then we also have sample problems on 454 and 455. Now these two pages I'll have to elaborate on one more thing. And so should be able to work on any of these sample problems and practice problems. And again, if checking the answers, if you've got questions, we can definitely talk about them. That is it for the calculations for the chapter. All right, one more thing that we need to do is, what if certain chemicals, we may have to do one more step in this calculation. So we've got two types of chemicals, non-electrolytes and then electrolytes. Non-electrolytes are covalent, electrolytes are ionic. If we're doing a calculation involving electrolytes, there is one more step in our delta TF or delta TB. We have to take into account the number of ions that are present. It's like more particles. The more particles there are, the more we have to do in the calculation. So here is all we do. We have to add, if it's an electrolyte, we have to multiply by the number of ions. So again, we still see our generic equation here. Delta T equals K times molality times the number of ions. So if it's salt, NaCl breaks apart into Na and Cl, 2 ions. Calcium chloride breaks apart into Ca and 2Cl, 3 ions. Aluminum sulfate breaks apart into 5 ions. So all we have to do extra is multiply by 2, by 3, or by 5. And that's it. That is the extra step. Here, if we're trying to rank, what's going to give us the largest delta T down to the smallest delta T? Biggest temperature change, electrolytes with a high number of ions, things like aluminum sulfate. Next would be electrolytes with a low number of ions, like salt. And then finally, the electrolyte or the chemical that would give us the least temperature change would be a covalent compound like sugar. Sugar is not a good one to use if we're talking about melting chemicals. Right. The last thing, and this really doesn't fit in, it's a great spot, so we'll just kind of talk about it here, osmosis. I talk about osmosis in biology, but simply osmosis is the movement of a chemical from a low concentration to a high concentration. It is opposite pressure movement. We'll talk more about this in electrochemistry and cells. So again, all we want to do is say the word and kind of talk about what it means. Osmosis just means if we have a chemical, it is going to move from an area of low concentration to high concentration of chemical, not pressure. Pressure would do the opposite. If there's a big buildup of pressure, it's going to try to get away. That's not the case here, talking about concentrations. Okay? So that's the extent of section 2. You got the calculations, and again, the constants given to you. You've just got to be able to work through that stuff. So then that is it for chapter 13.